Okay, we begin. First of all, any questions from you guys? Anything we should address in these hours today? Anything you find difficult, have problems with when it comes to MATLAB, programming, numerics, anything? No? Well, if you can think of something, then ask me or just interrupt me and ask. That's actually okay. We can take it on the fly as well. I will start today with a little trick when it comes to the publishing button, which then you are going to need when you deliver in your exercises. Because the assistants, they want one file. Of course, you could have zipped everything together, a whole bunch of MATLAB files, but then they have to actually run the program to see if it works, if you get the right figures, and so on and so forth. Publish, much easier. You generate one PDF file, which you upload. And that one should then include the source code and all the graphics. So now, just for test, I will write a big program that then we are going to publish. The program, say I want to plot the fast Fourier transform of the identity matrix 51 by 51. So that's my program. That's so-called a one-liner. So we can run this one. Untitled, that's a good name. And overwrite. And you get a very nice graph. So that's the fast Fourier transform for you. Not that that is important here. It's just a nice one-liner, as we call them. But say now I want to publish this one. So then you go to publish. And here, sadly, the default is HTML, web pages. So you have to change that one to PDF. On your computer, you can do it once. On this one, I have to do it every time. So now I can hit publish. Then he will run the code and then generate one PDF file, which then, as you can see, contains the source code and the graphics. So far, so good. So this one now you can upload as your answer to any exercise. Delete that one. Go back to the source code. And now say I have some questions for the student assistants. I have some handwritten notes, including my questions, that I want to also upload. How do you do that one? Because you are not supposed to deliver anything in paper here. So what do? You take a photograph of your paper. Here I have taken the photograph already. Is this one? So now say that's an image of my handwritten notes, which I want to include into the publish file, the PDF file. How to do that? Well, the name of this file is called download JPEG, and that one has to be located not in your working directory, which it is now, but I can show you here on this publish button, publish, and the setup here, because the default output folder, that is here some HTML. That's a sub folder where I am actually working. This is my work folder, so I have gotten automatically a subfolder, HTML. That's where you will find your PDF file afterwards. If you want to include the graphics, it has to be located inside that folder. So just close that one, back to the here. So there you see I have an HTML. So I take this one, Control X, and then I paste it inside here. So now I have the graphic file here actually next to the previous PDF file I just created some seconds ago. Now it should be possible to include it. How to include it? You go back to your source code, and it was a little messy, but at least I got this one to work. You have to start first with 2 percentage signs, and then 1, 1, and 1. And then in the middle there I had to take 1 space, and then what was the name? I've forgotten already. Download. Download JPEG. So there you have the file name. So that must be the syntax, at least in my version of MATLAB. Let's see if it works here. Double percentage sign, and then single percentage, and then 1 space before you have the syntax. Let's see if it works. Publish. There you go. So here now you can then have a picture of your sheet of handwritten notes, questions, whatever. Okay? You can have, of course, several images inside this one. Any questions to that one? That's okay. Last time we did this simulation of the planetary orbit using a forward Euler scheme. And yeah, this one worked quite okay. Just going to change the code here a little bit. Changing the X scale a little bit, and then we have a dot for every 50. I don't need that one. So this was now an animation of the Earth orbiting the Sun, or a satellite orbiting the Earth, whatever you want. And here everything is sort of non-dimensionalized. Oh, it didn't actually become circular. How come? Remove that one. Okay, then we go back to 1, 1. Why not? That's better. The problem is with the first order forward Euler scheme, it's only first order accurate. And although I know the answer is supposed to be a perfect circle, this one actually doesn't do the trick. You see, the Earth is moving away from the Sun. And it really doesn't help. You can have smaller and smaller time steps. The same will happen eventually. It just takes some longer time. What we did last time was then to use MATLAB's built-in ODE solver, ODE45. And actually we had some troubles there as well. But we had to increase the accuracy, and then he made it work. So today, instead of this classic forward first order Euler scheme, which then is written on the form, the new x equals the old one plus time step, and then here we had the velocity. So that's very approximative. Here it was the new, and here it was the old, and this one also was the old. So that is the forward Euler. It's explicit, so you know all the old values. You can easily create the new ones, as we did in the source code here. Here I had to write or specify another name, because if I overwrote the old x, then down here in this expression for the velocities, we would then have used the new x's, which is wrong. Everything on the right hand side, you might say, on the derivative should be only old values. So yes, we can do this. As you can see, it works. What I now want to show you is something called backward Euler. Backward Euler, or if you like, implicit Euler. I've heard some very good rumors about this scheme. It's supposed to be unconditionally stable, meaning you can take very big time steps and it shouldn't explode. That's nice. This forward Euler, he can be rather jumpy. With the big time steps, he's going to explode. So if we take a big time step here, say 0.1, it doesn't look too good. Planet has disappeared from the solar system. Not too promising. So the backward, what would now be the philosophy? Well, the derivative, x new minus x old divided by delta t, is of course the same. So the recipe, new equals the old one, delta t, but here everything on the right hand side should be not old but new. So this one should be the new value. Okay. So what is my equation system? Well, I have to rewrite it a little bit. If you look at the equations here, we have 4 of them: x, y, u, and v, position and velocities. And here on the right hand side, the velocities are old, positions here are old, radius, also the old values. Now I want to change that. So what is my equation system then? Well, I have to rewrite it and now say everything here, the multiplied with delta t, should now be the new values, not the old one. But then I have a nasty equation system, don't I? Just look at the x first. I just write it on the form everything new to the left. So here I will now have x, should be the new one, and then u, he should also be the new one. Throw him on the other side. So here minus delta t times u, and then on the other side I have the old values. So just to differ between new and old, I just write this one as old. Everything else is supposed to be new. So you see here one equation, 2 unknown. What about the rest? Well, the y will be exactly the same, just with v, and on the other side, right hand side, the old y position. And then we continue. U, and then here I now cheat. The constant gm, I put that one to 1, so I just drop him. I don't need him anyway. But I want the x and the r on the other side, so that should now be plus dt multiplied with, what will it be? Should be x over r power 3 equals the old velocity. And then finally v, also plus, but now is y divided by radius 3 equals the old v. So there you have the equation system. Now write it on a matrix form. How would it be? Well, you have 4 unknowns here. So we will have 4 positions, let's see, we do it like this, multiplied with all my unknowns, x, y, u, and v, equals, on the other side, right hand side, there you have all the old values, x old, y old, u old, v old, like that. Then the coefficient matrix. I will, of course, have all my unknowns represented. So it will be 1, 1, 1, and 1. You get the identity matrix, the diagonal. Of course we do. Here I will now have, for the y position, nothing. And then for u, minus dt, and no v. Here, no x. 0, I will have the y, no u, but I will have the v, minus dt, and so on. Here I will have x over radius 3, and then the y is 0, I have 1 for u and nothing for v. And finally the last one, y are 3 and 0. So this now is my coefficient matrix. So typically you write it on the form coefficient matrix A multiplied with the unknown x equals b, the right hand side. And that one can easily be solved in MATLAB. I'll show you. Coefficient matrix A equal, and then we just write it directly as it says, 1, 0, minus dt, and 0. On the other, 0, 1, 0, minus dt, x over r3, 0, 1, and 0, and finally y over r3, and 0 and 1. So that's my coefficient matrix. It's not constant. So, no, sorry, it's not x and y here. That's not correct, is it? Why didn't you tell me? He's multiplied with x already. And y. So it has to be 1 and 1. That's much better. Still, he is not constant. If he had been constant, he could have been put on the outside. Yes? DT. Do I miss a DT? Yeah, I miss a DT. Thank you. Thank you. None of you saw that either? You blind? Okay. DT and DT. If it had been constant, of course, I could have put this definition outside in the loop. But you see the radius. That's a problem. So I can't really do an backward Euler or an implicit Euler, but I cheat. We write semi in front. So this coefficient matrix is almost correct, but in the position r, that's taken now from the previous time step. So it's not entirely correct. That one should also have been included in the equation system, but as you can see, then it's a nonlinear system. You can't solve it then using linear methods. So more of that later. Okay, that was the A matrix. What about the B matrix? That is the right-hand side of the equation system. Well, that one should be the old values, like that. And then we solve the system. How do we solve it in MATLAB? You have a couple of options. Let's see now if we can do this down here in the command window. Yeah, this is my A matrix as it is now. Sorry. So we have the coefficients, and here we have some 1 over r to the power of 3 and so on. How to solve a system when you have it on the form in MATLAB. A times x equals b. Well, you can write it then A inverse b. So we want to have the inverse of the A matrix. And yes, you can do that and write inv A matrix. That's possible. So here you have the inverted matrix, and now you multiply this one with the b, then you have the solution. The MATLAB, they don't MATLAB creators, they don't recommend using inv. So we could have done it like this. Say the solution, what should we call the solution here? Big S equals inv of A multiply with b. That would now be the solution to my equation system. Yes, you can do that. Create the inversion of the matrix A first and then multiply with b, finding the solution. S will now be a vector of 4 values, which then will be our x, y, u, and v. Instead of using inv, they recommend using a backslash. Much more powerful, much faster. That one is highly recommended. Also, for huge problems, here is only a 4x4 equation system, or a 4x4 matrix. That's not a big deal. When you have huge problems, like 1 million by 1 million, you blow the memory if you write inv A. But using the backslash, he's very smart. He doesn't use that much memory. So backslash, that's a brilliant idea. Now we should be able to write x equals S number 1 and so on. Then we don't need those two. And we should be good to go. Have I done anything wrong here? No? Okay, let's try it. Do I... where? Yeah, thank you. That one wouldn't have been too good. Excellent. Okay, go back to the time step that we had, point 1. And now we call this one semi-implicit Euler. And run. Not faster. He has to solve an equation system now for every time step. But is he more accurate? No, he's not. And he goes the other way. Now the planet is going towards the sun. So the rumors that I heard, this one should be a much better scheme than the simple explicit Euler. Maybe that's not entirely true. But remember, both of them are of first order accuracy, so actually this one really doesn't help. What's nice with this scheme is you can take bigger time step. That's allowed. But that doesn't help at all. There we collided with the sun. So the accuracy is still very bad. First order. So if you take a large time step, large delta t, you have a large error. It's stable, but so what? So this one, no, it's really not a good idea in general. I know a lot of codes, they love this one because it's so stable. You can sort of do anything, it will not explode. But the results can be very poor. So use it with care. So this one is going to pop up in this week's lecture and also in the exercises to follow. Any questions to this one? That's okay? Yep.
If the simulation is running quite fast and you want to slow it down, is it possible to do that so you see what's happening?
If the simulation is going fast and you want to slow it down, yes, that's possible. Of course, the obvious thing, just to use a smaller delta t. If you want to sort of do the animation in real time, but you don't want to have a smaller time step, you just want the code to wait a little bit until he has reached the time step, yes, that's possible. You have something in MATLAB that is called, well, let's try now. Now he was running with 0.1 second for delta t. Let's see if we can make this one work. We have something called tick and tock. What should we call it? Time equals tick. And then down here, before we are allowed to continue, I say now while what should we write? Toc minus t. While that one is smaller than dt, we have to wait. I think that one should do the trick. Let's try it. Error. Didn't understand that. You must call tick without an output argument. No, he wanted the input arguments. Okay. Then we do it like this. T2 equals toc while T2 minus T, T2 equals toc. Maybe that one would do the trick. No, we didn't like that one either. I'll take without before calling. What's wrong with this one? Without an output argument before calling toc. That was strange. I don't get it. Sorry?
You let the t, so you just like tick without t equals.
You think? We can try. We can try. Then it has to be like this. That would be very simple if that one worked. No, that can't do the trick, can it? Yeah. Now you see it takes a little break. Actually, you can then simulate according to your clock time. So tick and tock, they are sort of stopwatches. So that's a trick if you want to slow down your animation to have the real time. Okay. Other questions? So we have 10 minutes. Let us do this one fully implicit. I don't want this semi. Maybe the semi was the reason why the simulation wasn't so good. I want to have full implicit. Save as without the semi, so implicit Euler. How can we do that? Well, this one is a little bit more tricky because I have this nonlinear equation system which has to be solved if you include x squared and y squared here as well. You can't use the backslash. That demands a linear equation system. We have a nonlinear equation system. How do you solve a nonlinear equation system? We can do that, but luckily we don't have to. If you have installed MATLAB with all your toolboxes, you have a routine called fsolve. I guess you know about f0. f0, you can find a 0 for a function with one variable. fsolve, you can find for n variables. So this is how we are going to use it. He returns the x. He returns fval, that is the evaluation of all your equations. Here everybody should be 0 if you had found a solution. Calling fsolve, he needs a function, and here he needs a guessing point. Some initial values, search for a solution in the vicinity of these values, which is convenient for us because we are having a time development code. So we have the values from the previous time step. There should be a very good guesses for this poor routine that has to solve this nonlinear equation system. So let's see how this one can be done. Yeah, we can leave the tick here, and that's okay. So now I want to have what? I want to have my solution vector S, and here we had something called fval, and then we had an exit flag. This is what the routine is supposed to return to me. Solution, evaluation of your equation, then the exit flag, that's something you can check. If it's 1 or bigger, then he has succeeded. If it's 0 or negative, he hasn't found a solution. So that can be a good idea to actually program. Then we have to write now fsolve, and inside here we have to put in a function. So let's do that. Function func, and then he needs a vector. Initial values, initial guesses, and then I give him x, y, u, and v. Well, actually, he doesn't need commas, I think. Only like that. But we have to create this function, func. So I copy my equation system. And then I want to have a new script. Function. Function, then you have to write this equation system on the form equal to 0. So how do we do that? Well, if we just do it like this, then you see we have written them on the form equal to 0. Then you have the solution. So this is the way you have to write your equation system to use this fsolve function. So he's going to return 4 residuals. The name was Funk, wasn't it? So, and here you will now have a vector. Call him big X. That's okay. So then we have to translate my X equals big X number 1, and so forth. Y equals big X number 2. U number 3. And V number 4. There we have it. Of course, you don't have to do this, but I prefer actually then I can use my equations the way I see them directly. So now I can write my equation system directly as it is. X minus dt multiplied with u minus, and then I need some x0. I need the old value. Next equation, y minus dt times v minus u old, and so on. U plus dt multiplied with x divided by, and here comes the pain. We have x squared plus y squared to the power of 3/2, like that. And then minus u0 minus u0, and then finally v plus dt times y divided by the same minus v0. So that should be my function. And this will not work, because inside this function he has no idea what is delta t, and these zeros, the old values, I haven't defined them yet. So somewhere he has to get them, and I give them to him by a global, not a global, but global. Global gives him access to the main script memory. I want to have dt, x0, y0, and so on. Then I take a copy of the global sentence. You need the exact same sentence also in the main script. So that should be okay. Save this one. He suggests the name Funk, that is okay. Then we're going back to my implicit Euler and insert the global sentence here. Not above clear all, then you're in trouble. Clear all clears the memory, so put it here. Okay. Then we can remove the equation system like this. So now actually this one should work. Let's try. Let's try. What was my time step? Fairly big. We try it. Nothing much seems to happen. What have I forgotten?
X0.
Thank you. The zeros, the old values. So now I just get the same solution over and over. I have to update the old values. So before I call this one, x0 equals x, y0 equals y, and so on. Let's try again. Oy, doesn't look too promising, does it? You get a lot of printouts from this routine. That's sort of the default. You can suppress it. Then you had to write, what was it? Optim set. Options equals optim set of display none. Then you can override the default and then use fsolve including options. You can have others in displays if you want. The fsolve routine is very complex, very advanced, and the source code is sort of a secret. You can't get it so easily. Remember, one of my colleagues, he actually met Clive Moeller, who has been developing MATLAB, one of them, and he asked him, could you please take this routine fsolve and put it in together with the ordinary MATLAB instead of having an additional toolbox for it? He just smiled. No, they want the money for it. So fsolve, a very advanced method. So if you want to have more printout just to see what he's doing, you can put something else here. I don't recall what. You have a long listing of all the steps that is involved solving this equation system. So let's do that one and then use a smaller time step. And I think that one was the first we had. So he's still a little bit slow, but he can manage. I mean, we give him very good initial guesses, the values from the previous time steps. So he's not too slow, but you see the performance is still just as poor as the semi-implicit. So it really didn't help. Still, it's first order method. Not good. But at least now it's fully implicit. So fsolve, very good routine, very strong. But for bigger problems, it's going to take a long time to find a solution. If you have, say, 20 equations with 20 unknowns, nonlinear, that can take some time. Here it's only 4 by 4, not a big deal. Any questions? Then we take a break.